Now let's understand the case setup for vortex shading. So one of the first things we need to understand about OpenFOAM is the folder setup. The case setup that you want to do for simulating any type of flow behavior requires you to place certain type of files inside each of these folders. There is a zero folder, there is a constant folder, and there is a system folder. Each of these folders constitutes of certain type of files which talk about the type of physics that you are dealing with or the type of solving that you want to do for your particular case. The zero folder primarily contains data about what type of field variables are you actually working with. This can be all the way from your velocity, pressure, density, temperature to something like your combustion with your individual species fractions, or it can even be something about the multi-phase flows where you have your individual volume fractions based on how many phases you are dealing with. For the current case, the type of files that we have, this is nu t, nu tilde, p and u. Nu t is your turbulent kinematic viscosity. This is the holy grail of what we are trying to solve for when we look for solving the turbulence problems. Next we have nu tilde. This is a inherent variable useful in calculations when using the Spalart Allmaras model. We'll talk about that in just a bit. We also have the pressure field as well as the velocity field. Now individually each of these files are going to contain data about at a particular patch or a particular boundary. What type of boundary condition are you actually using there? This is essentially an overview of what these boundary conditions look like. So the type of boundaries that we have, these are cylinder, inlet, outlet, top and bottom, and the front and back. For the most part, the type of boundary conditions that we have range all the way from a certain zero gradient to fixed value, so on and so forth. Let's try to understand what each of these are. And outright, I'll just say it, empty just means nothing, that there's nothing happening numerically in there. So let's start with understanding what these patches are and where they are situated. You have your inlet, you have your outlet, the cylinder, the top and the bottom. We also have the front and back. The assumption is that we just want to simulate a two-dimensional case. So the front and back are set to empty, as we can see here. Now, coming to what each of these conditions actually are, one of the first things that we see in any of the files is called an internal field. This is an initialization criteria, so to speak, in the sense that whenever you have your simulation running, right when it is about to start, you have to define what is happening to your field variables as soon as the simulation starts, or i.e. time is equal to 0. So if your domain is at time t is equal to 0, the pressure is equal to 0, every single mesh cell will be patched to this particular value, as you can see in this diagram. Next we have zero gradient. Zero gradient essentially talks about the gradient or rate of change of the property. Gradient of a field variable normal to that boundary being equal to 0 is what is termed as your zero gradient. The field variable at the boundary is essentially equal to the value just inside the boundary, in the sense that if we apply a certain zero gradient condition at the wall, whatever value was closest to the wall is what would be patched on top of the surface as well. The reason why the zero gradient condition is necessary is because many times, for instance, a certain outlet, it's easier for us to assume that the flow has reached a certain condition where the outlet is no longer a certain non-uniform, or it has reached a certain uniformity where the gradient just before the outlet and just outside the outlet is non-existent, so to speak. So zero gradient works out really well there. Next condition that we have, this is fixed value. This essentially talks about having a constant value for a field variable at your boundary. We essentially just set a certain value, a specified value at that boundary. For instance, if we have the inlet right there and we want to initialize the flow at 0.025 meters per second in this direction, we've just put that value. And notice that the velocity has three different components here in the I, j and k individual components right there. Next we have calculated. This is a important one for specific to turbulence. Calculated essentially talks about having a placeholder in OpenFOAM workflow where it is indicated that this value is derived from other field variables or other boundary conditions, so to speak. Specifically, this condition is not explicitly specified. You're not telling to the solver that this value exists at time t is equal to 0. Rather that, hey, Mr. Solver, you have to go back to your turbulence equations, how you're solving it. You have to understand how this particular value is getting solved in these regions and take that value, patch it on top of these boundaries wherever I've specified it. For our particular case, the large eddy simulation model that we're trying to use here, the new T, it is typically patched on top of your boundaries other than walls, and the value is going to be calculated with something like this. The individual nomenclature for what CS is, delta is, and S bar is given right there. Slip boundary condition. This is effectively used to model a surface where fluid can slide on top of a particular boundary. Earlier, whatever we've discussed, we talked about the no slip boundary condition where the fluid tends to stick to your boundary. This particular condition is useful for cases where you don't want the shear stress to be exerted by the fluid on top of your boundary, essentially simulating a certain free stream, so to speak. So if you have a no slip condition, you may see that the shape changes in this sense, whereas in the slip condition, the shape may not change. So that's where this is useful. Next, we have inlet outlet. This is specifically useful for patches where flow direction may change, specific to your inlets and outlets. It combines an aspect of inflow as well as outflow. Wherever you have outflow, meaning that flow is leaving your domain, the zero gradient condition gets put there. Whereas wherever you have flow entering a certain domain, the fixed value condition is going to be applied right there. So if you have an outlet, it is moving out of the body, there is your zero gradient. Whereas right at the outlet, if you have flow reversal, you may see that a certain fixed value gets applied right there on its own automatically. The user only needs to specify what is the inlet velocity and what is the condition that you've applied here, inlet outlet. Now, ultimately, we have the nu tu Spalding wall function. This is a wall boundary condition primarily used to model your turbulent viscosity near the walls. This is based on a particular Spalding's law, which effectively gives you a continuous profile of a relation between u plus and y plus, the non-dimensional velocity and non-dimensional distance away from the wall. Specifically for, from the wall to outer flow region, it is going to be a continuous function. It is suitable for both high Reynolds number and low Reynolds number flows and for turbulence models. The major criteria for using this particular wall function is best served for external aerodynamics, primarily for symmetrical flows. For complex flows, it may not work as intended. You may need a separate type of wall function, but for the most part with symmetric type of surfaces, this works great. Next, we have the constant folder. The constant folder is going to contain, for our purposes, only these two files, the transport properties as well as the turbulence properties. Transport properties is useful to define the transport properties of the working fluid. This includes how your viscosity is changing, how your density is going to be calculated. If it is heat transfer, then what's your thermal conductivity, certain other parameters such as your heat of formation, your specific heat, your Prandtl number, so on and so forth, wherever applicable. The turbulence properties file, this is useful to define the turbulence model that you are using. We particularly define the simulation type with laminar, Reynolds averaging, or the LES, large eddy simulations. And we provide the model coefficients if applicable. If not, then the default is taken right there. Finally, we have the system folder. System folder contains a bit more of these files. This is a folder that contains the major controlling sort of factors which influence your simulation. The first file that we have, this is block mesh dict. This is useful to create both the geometry as well as mesh for our current case. Then we have control dict. This is useful in controlling the simulation parameters such as your start time, end time, the delta t, if it is adaptive time stepping, what is the sensitivity, or in the sense that precision that you are looking at with respect to time, with respect to field data, so on and so forth. Decompose predict, this is useful while decomposing your domain so that you can run the case in parallel. So if you have multiple processors or multiple cores within your particular system, you can run the simulation in that number of cores, so to speak. Then we have the FV schemes and FV solution. Individually, each of these describe what type of equations are present and how they are getting solved. Primarily talking about FV schemes provides information about the numerical schemes that are used so as to resolve the type of mathematical terms that we are looking at. This includes your DDT schemes, gradient, Laplacian, divergence, SN grad, and so on and so forth. Also with the FV solution, this primarily provides information about how the matrices of your field variables are going to be solved, along with how you are going to precondition them so that they are as diagonal as it gets, so as to ensure easier convergence, better accuracy, so on and so forth. The other two files that we have, these are very specific to the case that we have at hand right now. This is noise dict, point and surface. The noise dict point file, this takes the data of the point noise source that we have already sort of provided in the control dict file itself, where we just say that these are the different observers around my particular cylinder, and I want to figure out what is the noise that is generated on these particular 4 observer points. The noise dict surface file, we have a .obj file, the primarily a sort of a sheet that is behind our particular cylinder. We are interested how noise is getting generated behind our cylinder due to vortex shedding on top of this surface file .obj that we have, and this noise dict surface is going to essentially solve for noise being generated on top of that one sheet.